Welcome back to Calculus AB. This is lesson 6.2. We're going to talk about something called Riemann Sums. This really piggybacks on what you learned last unit in lesson 5.6. Remember the idea of signed areas using definite integrals? So once again, if I were to give you, like, here's the function f of x. I asked you to take the integral from a to b of f of x dx. Then here's a, here's b. I'm really saying this is the area. It's signed because this is above the x-axis, so this area is positive. Remember that stuff? Well, unfortunately for you and I, not all such areas can be found that way. Some functions actually cannot be integrated. They're said to be non-integratable. And sometimes you're given a data or a graph, but not the actual function f of x in its equation form. So if you don't have that, what do you do? Well, you can't get the exact area, but you can find an approximate area. And in this lesson, we'll use different methods of approximating. And we'll do this by really just adding areas, and in this lesson we'll focus on rectangles. And this sum, or this addition of all these rectangles, is called a Riemann sum. So here's example number 1. Notice I'm asking you to approximate the integral from 0 to 10 of f of x dx by adding the areas of the 5 rectangles shown. So once again, there's no function here for this crazy graph. There is a graph with a grid and a corresponding table of values, and they have decided, or someone has decided, to break up this curve into 5 pieces, and we're going to decide to use rectangles to approximate. Now notice here that for each of these rectangles, it looks like they chose the midpoint value to determine its height. The midpoint value of 5, right, to determine the height of the third rectangle. The midpoint value of 7 to determine the height of the fourth rectangle, and so on. So that's why they say this is the midpoint Riemann sum. There are 5 subdivisions, or 5 rectangles of equal width, and then the heights of these rectangles are determined from the midpoints of the intervals. So really, someone has chosen to use the midpoints. Is that a best approximation? Hard to say, but it is an approximation. So let's try it now. Using that first rectangle. So really what I'm saying is let's take the integral from 0 to 10 of f of x dx. Okay, this is approximate, so I'm not going to use the equal sign, but the squiggly equal sign. The first rectangle here, the base has a width of 2, the height is 2. There we go. The second rectangle here, the base is 2. The height seems to be 5. The third rectangle here in green, that's 2 times 3, and so on and so on. So 2 times 1 plus 2 times 3. You can then add this all up. 4, 10, 6, 2, and 6. How about 28? So 28 is my approximate area underneath this curve. Now, in this example, and in many of the examples, the rectangles used to approximate areas are of equal width. Notice each one of these had an equal width of 2. In such cases, you can actually develop a formula to find the Riemann sum, because the widths are always the same. So in this case, the widths are the same. I can just factor that out. So look, I could have factored out 2 from each of these, and then just added all the different heights of each of the rectangles. See? Height, 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 height. That's height, 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 height. Okay? Note the number of heights will also equal to the number of rectangles. So in our previous example, there were 5 rectangles, so there were 5 heights. And notice that the width, because they are equal, is always defined as the difference in the b minus a, or the actual width of the entire definite integral, divided by n, which stands for the number of rectangles. Okay, so In this example here, our width was what, b minus a, so 10 minus 0, divided by n, which was 5, so of course that equals to 2. Cool? Now, remember what I said earlier? We didn't have to choose the midpoints for the heights. We could have chose other methods to do the heights. So in example number 2, I'd like you to approximate the same integral, this time using 5 rectangles of equal width, so just like before, but now it says using an upper or circumscribed Riemann sum. What does that mean? Well, that means the heights of the rectangles are determined by the upper or largest f of x value, the largest y value in each of the intervals. Okay, so let's go ahead and figure out our width first. Width would be b minus a over 5, that's still 2. So now I know I should split up my interval here into widths of 2. And now within each of the intervals, I want to find the highest or largest y value. So between 0 and 2, the highest y value is 4. And I'm going to use this to approximate the area. Maybe not so great, but hey, it's a method. So let's try it now. The integral of 0 to 10 of f of x dx, once again, is approximately. And in this case, because we have equal widths, I'm going to use our lovely formula from above. So width would be 2. And now let's look at the height. So the height from rectangle number 1, the one in red, the height here is 4. Now in rectangle number 2, the height I'm going to use, once again, the highest y value would be 5. For number 3, the highest y value between 4 and 6 occurs when the x value is at 4, which just means that the y value is also 4. And then between 6 and 8, the highest y value seems to be 2 throughout this interval, plus 2. And then finally, between 8 and 10, the highest y value is 5. You can tell that this is totally going to be an overestimate, but still, it is an estimate or approximation. 4 plus 5 is 9, plus 4 is 13, plus 2 is 15, plus 5 is 20. This is 2 times 20, or 40. Okay? Same question, different way of approximating, totally different answer. Okay. Take a look at the next page. Some more examples for you to try. This time I think I'm going to leave you to try 3, 4, and 5. Okay? Actually, maybe 3 and 4. I'll come back to help you with 5. Alright. Notice in this case the lower or inscribed Riemann sum, meaning the lowest y values. Lowest y values in the interval. Okay? Notice in number 4, the right-hand one means you're always looking at the right endpoint and using the right endpoint as the y value for each of your intervals. Alright? Your turn. Go. Remember approximation again. The width in both of these examples, I think, are still the same, 2 units. Now this time, the lower one in this case would be 0. From 2 to 4, the lower one would be 4. The lowest one from 4 to 6 happens to be the y value of 2. The lowest one between 6 and 8 is 1. The lowest one between 8 and 10 is 2. So this totally is an underestimate, but once again, still a estimate. Try number 4 now. Same idea. Don't forget the approximation. The width is the same. Now this time I'm always going to use the right endpoint. So for the right endpoint between 0 and 2, its y value is 4. The right endpoint between the interval from 2 to 4 is when x equals to 4, which gives a y value of also 4. So there we go. Oopsies, what did I do wrong? Ah! I did not look this carefully. 10 subintervals. Ay, 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 ay. Get ready to add a whole bunch of numbers. So the first interval, 2. The second interval, the right endpoint here, would be at 4. At 3, it would be at 5. At 4, it would be at 4. At 5, it would be at the y value of 3. From 5 to 6, we're going to use the right endpoint, so at 6, the y value is 2. From 6 to 7, we'll use the right endpoint at 7, the y value is 1. I hope you get the idea. I'm getting tired of talking. Yikes. Add up all those numbers. 2 plus 4 is 6, plus 5 is 11, plus 4 is 15, 3 is 18, 20, 21, 23, 26 plus 5 is 31. 1 times 31 just gives us 31. Alright? Now, notice number 5, I did give you a function, but if you wanted to try to anti-differentiate this function, good luck. And that's why I'm going to ask you to try to approximate this integral with a midpoint Riemann sum, this time using 3 equal subdivisions. So with 3 equal subdivisions, I'm going to take the difference in my b minus a, divide that by 3, my width will be 2 units. Notice the width is 2 units, and I'm using the midpoint sum. I'm really looking for this value right here when x equals to 1. Okay. And that would be my first height. So let's try this out this time. Approximation once again. The width is 2. And my first height would be when the x value is 1. That means I can plug it into this expression to find the y value. 1 squared is 1. 1 plus 10 is 11. So my first height here is root 11. And once again, I found that by taking the x value and plugging it into my expression. For between 2 and 4, I guess I'm going to try to use my x value at 3 to figure this out now. So I'm going to plug in 3 into this expression. 3 squared is 9. 9 plus 10 is 19. So this is the square root of 19. And then finally, from 4 to 6, this is the midpoint again. So I'm going to use this value of 5. It looks like 6. Is it really 6? Well, it's close enough. 5 squared is 25. 25 plus 10 is 35. And that is my answer. Okay, I'm not even going to go ahead and try to calculate decimal. You can do that if you have a calculator. Now, the one little trick sometimes, or weird thing, is that it is possible that f of x is not always greater than or equal to 0. So they could be negative. Or that your subdivisions do not produce intervals of equal width. No one said they had to be equal width. Regardless of how that happens, you can still approximate values for definite integrals by using Riemann sums. And I've seen questions like this on the AP exam where the widths are totally different for each interval. So in this case now, for our last example here, can you approximate the integral from negative 10 to 5 of this function, 2 to the power x minus 8, by using 5 right-handed rectangles, yet whose widths are determined by the interval separating the following x values? You're like, what? So our first interval goes from negative 10 to 4. So notice that it is pretty wide. The interval length here would be 6 units. Because I'm using a right-handed rectangle, I'm asking you to use the x value of negative 4 to calculate the y value for the rectangle. And notice the y value here is below the x-axis. So this will be signed area, and this signed area will be negative. So let me show you how we can write this out. Let me copy the question. Approximation again. And notice I told you it's 6 times the height. And the height is given by the x value of -4, which I will plug into my expression. So that'll be 2 to the -4 minus 8. Okay? Next, going from where? From -4 to 0. So now I'm going here to here. Our width here is 4 units, but I'm using the right-hand rule. So once again, I'm going to use the rightmost x value, in this case 0, to help me calculate the height. The width once again is 4. The height is 2 to the power 0 minus 8. Continuing on, okay, I hope you get the idea, and I'm just going to do one more, and I want you to finish off the rest. I'll use green this time, from 0 to 2. So from 0 to 2, the width is 2 units. I'm going to use the corresponding y value at the right-hand part, which would be the value of 2, and there you have it. And then going from 2 to 3, that's this here, so just a unit of 1. I think that's just 2 to the power 3 minus 8. And then from 3 to 5, that'll be from here to here, width of 2, using the right-hand endpoint. I'm actually asking you to do that. So plus 2 times the right-hand endpoint would be at 5, so 2 to the power of 5 minus 8. I'm not even going to calculate this out. You can do it, but this is the idea. Okay? If you understand this concept, you're well on your way.